Good day. My name is Osu Kwame Ketia from Group 22, and we are here to find the transfer function of S of x over f of s for the system below. So this is the system. So we have the damper, which is f of v, the coefficient. The damper opposes velocity, and we have the mass itself. So this is the object where the damper opposes the force on the object, and then we have the spring which opposes displacement, and also we have the net force. Okay, so this is the object. There are three forces acting on the object, which is the net force, and then the force here, the damping force, which opposes velocity, and then the spring force, which opposes displacement.
From the diagram, Fv represents the damping coefficient. Where the damping force opposes velocity. K represents the spring constant. M represents mass or the body. F of t represents input or applied force, and x of t represents displacement.
So from the information provided over here, I'm going to talk about the forces acting on the system. And according to Newton's second law, the sum of forces acting on the system is equal to the mass times the acceleration. And the acceleration is the second derivative of the displacement. So with the two dots on top of the displacement, it shows that that's the second derivative. So right now, the forces acting on the system, we have three forces acting on the system. The first force is the one applied to the mass in order to cause the acceleration. That's F of t. And this is, that's F of t. And then the second force is the spring force. Is the spring force, and this is equal to negative k x of t. And then we have the damping force, which is equal to negative the coefficient times the first derivative of the displacement. So the negative attached to the spring force shows that the spring force moves in an opposite direction to the displacement. And here, the first derivative of the displacement is the velocity. So the damper force is equal to the constant times the velocity. And the negative shows that it moves in the opposite direction to the velocity. So according to the Newton's second law, the sum of the applied force, the spring force, and then the damper force is equal to this. So So m second derivative of the displacement is equal to minus k of t plus f of t plus minus k of the first derivative of t, which is the displacement.
The sum of forces is equal to mass times acceleration. So applying Newton's second law, we have m of x of t is equal to f of t minus k of x of t minus fv of x of t with a dot. Rearranging, I'm going to make f of t the subject. So we get f of t equal to mx of t with a double dot plus ax of t plus fv x of t. Like this.
Yeah, so from this expression, we are going to find the Laplace transform of this expression. So f of t will become f of s. Then for this, the mass will be the same, but for x of t, the Laplace will be x of s. Then for the first derivative, it's going to be s x of s minus x of 0. Then for the second derivative of this, it will be s squared x of s minus s x of 0 minus x prime of 0. So we'll substitute this into this expression. So f of t will become f of x. Then we have the mass times this expression, which is x squared minus x of 0 minus x prime of 0 plus k into brackets x of s plus fv into brackets s of s minus x of 0. And from a linear time invariant system, we know that the initial conditions are 0. So this will be 0, this will be 0, and this will be 0. So you have f of x to be equal to ms squared of s plus k of x of s, then plus fv of x sf of s.
In finding the transfer function of this particular system, we know that all initial conditions are set to 0, right? And in this particular system, we know that the input is directly proportional to the output. But in this equation that we have here, it shows that there is an internal energy inside the system, and therefore we can't find the direct output from the input. So what do? We set the initial conditions to 0, and by setting these initial conditions to 0, we eliminate any internal energy in the system. So after setting the initial conditions to 0, we get this equation, and this equation is telling us that our input is giving us a direct output. If we didn't do that, we'll find out that in this system the mass was already moving, and then the spring was already compressed, and that won't give us the desired output that we need. Thank you.
So since the transfer function is in the form x of s over f of s, we'd have to factorize x of s out of this equation. So then you have f of s being equal to x of s squared plus x of s a plus x of s f of v s, and then you divide by x of x, which will give you f of s all over x of s being equal to m s squared plus k plus f of v s. And then since this is the form of the final answer or the transfer function, you'd have to reciprocate to get the same format. So then your answer will eventually be x of s all over f of s being equal to 1 over m s squared plus k plus fvs.
In conclusion, to find the transfer function of this linear time invariant system, where Fv is the damping coefficient, K is the spring constant, M is the mass, F of t is the input, and X of t is the displacement. We use Newton's second law of motion, which states that the sum of forces is equal to the mass times acceleration, where m of x of t is equal to f of t minus k of x of t minus fv of x of t. And using Laplace transform, we got f of s equal to x of s of ms squared plus x of s k plus s of s fvs. And factorizing x of s, we get f of s over x of s equal to ms squared plus k plus fvs. And since the question states that we should get x of s over f of s, we reciprocate it to get 1 over ms squared plus k plus fvs.